that graph is probably familiar to a lot of you here. It's the Keeling Curve, which shows the concentration of carbon dioxide in the atmosphere, measured in Hawaii and cross-checked in other places as well. Interestingly, the oil companies tried to stop the funding for that back in the early 60s, but Keeling managed to keep going. You'll notice that there's a fairly remorseless acceleration on the upward curve. There's lots of little jiggles as well, and we've just finished going past the bottom of a jiggle. That's on the date of the 30th of September, and at that point the level was 400.91 parts per million. And the grim thing about this is that it's like the 4-minute mile. We'll never go below 400 parts per million again unless there's some really brilliant chemical engineering to suck CO2 out of the atmosphere. And the result of all that has been the rise in temperature, particularly in the winter in the northern part of the world. You can see that we've got a temperature anomaly in February 2016 of 5 degrees Celsius in a lot of this area here. And that's doing rather bad things to the Arctic ice. This was the ice concentration in the North Pole. There's the North Pole there, there's Greenland. And you can see there's an awful lot of really rather empty sea going on around there. This bit is the North Pole where the satellite wasn't covering properly. There's a bit of thick stuff left here, but this is getting really dangerously thin, maybe 15%. Another way of looking at that is to look at the volume of ice, not just the area. Starting from 1980, this is the amount that's left in September, and this is the recovery of it by March, okay? And you see we're wiggling down rather dangerously to having no ice at all in the end of the summer. Another grim way of showing this is this spiral, which is giving you years round here, 1979, 1980, and then the different colors are months. Okay, so time is going around like this, and we're spiraling inwards. And the black one is the end of September, and you can see that we're getting nearer and nearer to zero. And when we're losing the surface ice, instead of looking what you'd expect to look at, this is the place in Greenland, because the top layers are melting, they're leaving behind all the black carbon and the volcanic ash and the mess that's underneath the top layer of snow. And so this is getting very black, absorbing a lot of heat. And that's melting a lot of water. And the result of that is that the water here is running down through holes in the big ice cap, and it's beginning to float the ice cap. And it could suddenly start sliding if we put enough water underneath it. There are a lot of computer models about how much ice there is and how fast it's going, and they're nearly all complete rubbish. This is a whole collection of them, and they're all saying, oh, nothing to worry about till 2060, but the reality is this black one. And there is one computer model done by a chap called Maslovsky in the United States Navy, which is predicting this going down to zero in 2018, 2020. Now, when you lose the Arctic ice, you lose a lot of the reflectivity. Lots of heat is going to be going down into the Arctic Ocean, and it's going to be melting the permafrost at the bottom of the Arctic Ocean, and that's going to be releasing methane, and methane is a really much more dreadful greenhouse gas than CO2. It doesn't last as long as CO2, but in the first year it's about 250 times worse than CO2. So we could be getting a great big belch of methane coming up out of the Arctic shallow seas. So this is all rather worrying, and people have been thinking about what could do about it. And one chap who came up with an idea is called John Latham, and he wanted to use a thing called the Toomey effect. And that's a chap called Sean Toomey, and he had an interest in why clouds appeared to have different brightnesses. Some were grey and some were white. And his work was started off by these funny ship tracks that appeared in, this is the Bay of Biscay. They sometimes come in the Pacific. They don't always come, but sometimes they do. And he's very interested in why you should get this long white streak behind a ship. That's the Isle of Wight, and that's the Bay of Biscay. And he worked out various bits of, lots of observations and measurements of the whiteness of a cloud. And he came up with an equation like this. The brightness, the albedo, he called it, depends on the depth of the cloud. That's pretty obvious. The amount of liquid water in it, and the number of condensation nuclei in a cubic centimetre. Better tell you what condensation nuclei are. If you have water vapor that's above 100% humidity, and it would like to condense down into a liquid drop, it can't do that unless there is a tiny little nucleus seed for it to start growing on. And a chap called Kohler worked out what size of seed you needed for what sort of chemical and what sort of humidity change. And he explained why we need to get a little bit more. Now, in this room, in each cubic centimetre, there's probably about 1,000 little nuclei of smoke or dust or something. So if you boil the kettle, the drops of steam can form very quickly. But in mid-ocean, the air is very much cleaner because things have been falling and been washed out. And there's maybe only 50. And that bit of algebra says that if you double the number of nuclei, the reflectivity of the cloud goes up by about 0.05, okay? And you double it again, you get another 0.05. So it's a logarithmic. And to demonstrate that, I've got here some 4mm glass balls, and I've got some 40 micron glass balls, and you will see that these are quite a lot whiter than those ones. And there's a grayscale behind there. You can put all that algebra together, and you can get this graph here. What we've got is the CCN concentration. These are the little smoke, dust, whatever, particles here, going from very, very clean air, 10, to 100, to rather dirty air here. And we've got cloud reflectivity here for different cloud depths, okay? And the middle range for the clean air in the middle of the Pacific is round about there, and then the dirty place in the Atlantic is here. And the reflectivity is 0.2 going up to white there. So for a lot of range here, this is where that Toomey equation is working. And what you want to know next is what the condensation map, concentration map is. And you see there's a lot of area around all these blue things where it's only 50 to 75 per cubic centimetre. John Latham's idea was to spray tiny drops of filtered seawater out in the mid-Pacific, and he wanted to have them below 1 micron, 0.8 micron, and he wanted to have these just released into the turbulent layer of the boundary layer over the sea. When the wind's blowing over the sea, there's lots of eddies, and he'd want these to be shifted round evenly, more or less evenly, through the boundary layer, and the ones that got up to where there were clouds would they would increase the number of available nuclei there. So instead of having liquid water as maybe a 25 micron drop, that would turn into 2 19 micron drops. And if you work out the area of reflecting material here, 2 19s have a bigger area than 125. Actually, it's a hell of a lot more complicated than that, but that's nearly right. And if you then put all that together, you put all that together, and you can draw a graph like this, where we've got the amount of spray we're spraying. It's got to be tiny drops, and these are cubic meters per second. And here's the amount of cooling we're going to get for the world. And the circle here is about the damage we've done up to now, and the question mark is what would happen if we were to double CO2. So the amazing thing is that spraying about 10 cubic meters of water a second would undo all the damage we've done to the world up to now. Now, what we need to do is clean air. We need lots of sun, the right side of cloud, fairly low down, and there is a map of where we think it's good places to do it. The red is really fantastically good. The yellow is pretty good, and you can see that the places to do it are different in different times of the year. An interesting thing is that it's actually more solar energy going into the North Pole in midsummer than going into the equator. That's an astonishing thing, but if you work out the sine of 23.4 degrees over 24 hours, that gives you a bigger number than the integral of 0 to 180 over a shorter time. So my job has been working on the engineering hardware to do this, and this is the present design. There is a ship, a hydrofoil ship here, which is not, it's flying on these wings here rather than floating, and these hydrofoils here have got a variable pitch, so we can have the force on them increased or reduced by changing the pitch angle of the foils. And we've got, the way we work is we have opposite pitch changes fore and aft, like that. So that's going up and that's going down. So it's trying to rock the boat like that. But the aft one is doing the opposite. So we're putting a torque across the hull in the middle, but we can do work as these moves up and down. We are driving these, they're sailing boats. Instead of having textile sails, they are using things called Flettner rotors. This was an idea from the 1920s. Anton Flettner was interested in making more efficient sails, and he built a ship with Flettner rotors, raced it across the North Sea to Edinburgh, to Leith, and then he went across the Atlantic to New York, and everyone thought this was wonderful, and he got orders for 6 more boats, and then the 1929 depression came along and they were all cancelled. They are actually being built again. The big thing about them is that the thrust on a Flettner rotor, it has to spin, by the way, I should have said that, it's spinning rate. The thrust on it is about 10 times higher than the thrust on a sail, but they're much more computer friendly. You can control them with a computer very nicely, and I want to have this unmanned. This wants to be remote, so we don't worry about food and water and medical supplies. So these things are cruising the ocean. They're sending messages back to the world's best meteorologists about what the conditions are. We're measuring that with a satellite. We're deciding where these things ought to go, and we are directing them there so that they can take into account what monsoons are doing and what El Niño is doing and all that stuff. The linkage here is giving you the same effect as the suspension on a road vehicle. When we had carts with no springs, it was pretty uncomfortable going even slowly, but now with the right sort of shock absorber and suspension, we can go much, much faster. And that's going to do the same job for that ship. The most difficult, challenging problem is to filter the seawater to get rid of all the plankton. And to do that, we want to use things called ultrafiltration, which is used to clean up the water that's going to be used in reverse osmosis desalination. And there's a big, big industry now. Desalination is even more stringent than our requirement. So we have to get super clean water filters. And the way we do this is we have a bank of 8 of them, and one of them is always being backflushed. So you use some of the water from the main ones to backflush one of them, and they take it in turns. And every few minutes you say, right, it's your turn to get backflushed. The engineering design looks much too complicated for fine details, but I just want to put that up so you can see that it's there and has been done. There's a lot of algebra, a lot of computer models backing that up, and this is an even more complicated block diagram of all the power flows. So, what are the objections to it? A lot of people say, oh, it'd be terribly expensive. Well, actually, if we look at the cost of corvettes in 1940, a Royal Navy corvette in 1940 was built in the same sort of numbers, and it had quite a lot bigger displacement and a bigger power, but it's an example of what it might be. They cost £60,000 in 1940, and if you do the index linking up to that, it comes out about 2.5 million. Now, we want about 300 of those to offset all the damage we've done up to now. And so we're talking about maybe a billion, 900 million to a billion. And if you want to borrow £1 billion to buy a fleet of these, you have to pay the banker interest rate. Now, at the moment, the bank's interest rate is ridiculous, but I would have thought you could probably get 10% would be a good investment to write it off over 25 years. So that means that we're talking about maybe £100 million a year, only £100 million a year, to undo all the damage we've done up to now. And I found out that the cost of the Paris conference, which was signed recently, was more than that, 130 million. That's the number that's been released by the French government, and I don't know yet whether it was just what it cost the French to have it, or whether that's including sending Barack Obama and all his security guys across. That's one objection. It's going to be cheaper than the conferences. The second objection is that if you suddenly stopped it, the temperatures immediately go back to, well, it wouldn't immediately, they'd take about 2 to 10 years to go back to where they would have been. And when you think about how long it would take if you stopped generating electricity, that's terrible trouble in a fraction of a second. If you were to stop water treatment, that's terrible trouble in about 2 days. I would much rather have something that I could stop and reverse. Let's say that there's a sudden extra volcanic eruption, and that will cool us down, so we want to be able to turn it off. The other thing that's very depressing is that people say, everything that we always do, it always goes wrong. I mean, putting rabbits into Australia was a terrible mistake. Now, actually, we amplify all the things that go wrong. We really magnify those. Actually, putting horses into America was a pretty good idea. We wouldn't have had any Western films without that. So I think the objections to this are really not really well thought out. And it would be great to have even a tiny bit of money to actually start designing and building and testing the hardware. And that's my 18 minutes. Thank you.